thanks and welcome everyone to this SMRI Algebra and Geometry online seminar today. We're very happy to have Magdalena Boos, who works at the Ruhr Universität Bochum, but who is actually joining us from Münster on what is early in the morning her time. So thanks very much for agreeing to speak at this time later. And we're looking forward to your advertisement about symmetric quivers and their representations, please.
Thank you. Yeah, I'm very happy about this invitation, Anthony. Thank you. And that I'm able to talk about this advertisement of symmetric quivers. And let me say that just yesterday we put the article in the archive, so this is a good day. So I will tell you about our new article and about kind of everything around it. This is supposed to be an overview, advertisement, introduction talk, and technical details gets very technical very quickly because we have to deal with forms and stuff. And so I will mention it, but not show you all the deep technicalities. And then if you're interested in them, of course, you can write or look at the literature, or we can figure this out. Okay, this was partly worked out in Rome, where my co-author Giovanni Cerulli Irelli works, and I was granted a 6-month stay, which was amazing. Of course, I mean, imagine to work in Rome. You work in Sydney, so you are pretty lucky too. And so get into the pictures now. Imagine Rome, it's nice, it's beautiful, the sun shines and there's gelato, and then we can start with the advertisement. Okay, and I want to show you the big picture before. We start on the bottom here. That's representation theory, and I want that's fine. And this is where I come from. This is my love, my passion, my home, kind of. And when I say representation theory, then I mean associated algebras and quivers with relations. And then there's a nice connection to algebraic geometry of these quiver representations, grabbing the representation category and looking at it as an affine variety, which we will see later. So we have a method from algebraic geometry at hand too. And there's a further connection because in my research, I want to also look at algebraic Lie theoretic questions. And in particular, this means that we look at group actions of some classical groups acting on some subvarieties of the Lie algebra of G. And since there are algebraic groups and affine varieties, also we have this connection from the algebraic geometry to the algebraic Lie theory. And so kind of these fields are intertwined anyways, you know this. But in particular, for our questions, we are interested in 2 goals. So our goals are, can we describe the orbits and the closures of the above? Something very simple, something very nice to know. And we are lucky because we are able to prove that in the type A, we can find a translation via an associated fiber bundle to the usual representation theory of a quiver. And this was what I did for a longer time. And then I was asked all the time, and what about the other classical Lie types B, C, and D? What about them? And I just didn't know. So I was kind of annoyed by these questions. But luckily, we found a connection too. And this means that in the other Lie types, we go over to the symmetric representation theory. Okay. And these translations are associated fiber bundles, which we will not see, but kind of see. And via these translations, the orbits are given by isoclasses of representations, and the closures are given by so-called degenerations. And by looking at these, we will in the end be able to understand the results. So let's see how we work. We start with the motivation. So this is the first part of the talk. Then I'll show you the translation in type A to usual representation theory. Then afterwards, we have to understand what is symmetric representation theory in order to say something. And I can show you the translation and the classical types. Okay, and then afterwards in 5 we will look at methods, because we have quite a few methods at hand in representation theory, and we can make use of them. And then in 6 I will explain what degenerations are, and then in the end, results. So that's the plan, more or less, for the talk. And this means that we start with the algebraic Lie theory. And now this is a motivation, and we draw a picture. So we fix some natural number, and now I draw the picture in this. You will see that it will be colorful because I'd never worked with slides. I like the blackboard, but this is a nice way to be creative, I guess. And so let's see. We fixed an nilpotent cone. So we start with a usual nilpotent cone in tape A. So we have n times n nilpotent matrices. And on these, of course, we have a group action of GLN, and that's change of basis. So conjugation, G and G inverse. And this is classical or a very standard action. And the orbits are known by Jordan normal form, and the closures are described by Gerstenhaber, and this is this box dropping of Young diagrams. So this is known, but it's not known if we restrict further. So now restrict on the right-hand side to kind of a small subvariety. This is the subvariety of 2 nilpotent matrices. Even if we square them, they are 0 very quickly. And on the left-hand side, we fix a Borel. And then again, we have the conjugation action. This is induced by the above one. And what I told you before is that we have 2 questions about this. I mean, we have many questions, but we have to start somewhere. So we start with these 2 questions. The orbits, can we just grab them? And the closures. So the closures are given as union of orbits. We have to find all of the orbits in the closure. So this is type A. And then, of course, we are asked, what about the other classical Lie types? And this means that we modify the picture and we put them in. So what does this setup mean for the classical Lie types? In types B, C, and D, we fix a G classical, so a symplectic or an orthogonal subgroup of GLN. And then here, the Lie algebra is denoted by this small weird g, which I'm not able to draw very properly, but I guess you can see what this is supposed to be. And of course, what do we have to do with a nilpotent cone? We intersect. So now we look at nilpotent matrices, which are symplectic or orthogonal. And again, we have the conjugation action. And also this is known. The orbits are given by Springer-Steinberg and the closures by Hesselink. So this is all known. In the lower part, however, we restrict the Borel to G, and then we're lucky because this again is a Borel. And on the right-hand side, we only fix the 2 nilpotent symplectic or orthogonal matrices. And then again, we have the conjugation action. And this is not known. So the orbits and the closures, not known. We know that there are finitely many, that's for sure. But what about the description? And this was the start of our project. So, of course, the questions now, they're the same in the middle part, describe the orbits and the closures. But there is one particular interest that we have in this picture. And this means that if we know the outer part, the type A, and we are interested in the inner part, can we just be stupid and restrict? This will be so much easier than to start calculating again. And so this is what I mean by inducedness. If we know the outer part, can we just restrict and we have the inner part? Is this induced directly? And this is not clear. And this is actually very difficult for orbit closures. I mean, we don't know how it works. So maybe in the end we will think, ah, of course. But in the very end of the talk, we will see what we know so far about this. And I don't want to spoil it now, so you can be nervous now. Might it be true? Might it not? Okay, this is our motivation. This generalizes of the parabolics to different subvarieties in the Nilpotent cone. We can think of further setups, and also did and worked on this. And then for some actions, it relates to certain Hilbert schemes, and for some there is the enhanced Nilpotent cone involved. And so this is so very basic, and that's what I love about it. That even the motivation is, why shouldn't we look at this? It's a Borel action. Okay, and now we want to see how this can be translated to representation theory. And so, no, first, see. So in the above, I told you what who worked it out. In the lower part, you will see it in this talk, and in the upper part, we know that it is in fact induced. So if you have the Young diagrams for the orbits, then you just grab those who have the symplectic form orthogonal structure, and you're done. And the same holds true for the closure relation. This is amazing. Okay. First we fixed this, we finished this, and now let's look at, okay, we do the second one. We should start with the translation. So we define. We want to go to quiver representation, so we define a quiver, and that's the one. It's very long. It has 2l+1 vertices. It's linearly oriented from left to right. I gave names to the arrows, which will make a difference now. And in the middle, we have a loop. And then we look at the path algebra. So actually, we don't need this path algebra in the talk, but I thought it's nice for you to have seen it at some point. The path algebra is defined as an algebra like this. As a C vector space, we span it by all the paths in Q, all possible ones. So we have infinitely many at the loop, for example. And the multiplication is given by concatenation, if that's possible, and otherwise it's 0. This is the path algebra. And so we have an algebra, we can fix an idea. And in our case, we fix the idea. So this shall be 0, going from this vertex to this vertex, and 2 times the loop is 0. And there you see 2 times the loop. So this is true nilpotency. Okay, so we encode our problem. This is what's called relations, the idea. And now we get the quotient algebra, and that's the algebra we work with. And the nice thing is it's associative algebras, and it's also finite dimensional, because we got rid of these infinitely many loops, because 2 times the loop is 0 already. Okay, and now we look at representations of this quiver. We fix the quiver, that's the same. And we have these relations, which of course play a role in the representation theory. And now we fix a vector, and that's called a dimension vector. Now it's just a vector, but we will see why this is a dimension. And it's 1, 2 going up onto L, then N in the middle. That's the size of the matrix that we started with. And then L going down again to 1. Okay, so you see that's kind of a flag. And now let's look, what is a representation of this quiver? At the vertices, we put vector spaces. And we just, in this example, we just grab C up to the something. And then for the arrows, we fix C linear maps. So each vector, each arrow corresponds to C linear map. And then we encode, just collects the maps as a tuple, fulfilling the relations. Of course, the representation has to fulfill the relations. 2 times the C linear map, and then going from here to here, and this arrow, and then this is also supposed to be 0. And this is what's called the representation variety. Now we have to understand morphisms between representations, and so we grab a second representation. And if we want to understand the morphisms, we just see in the picture already what has to happen. We have a tuple of the vector spaces at the vertices. So here, here, to here. Okay, like this. So we have all these maps from the above one to the lower one. If they're all isomorphisms, then it's an isomorphism, and if they're not, then it's a morphism. And of course, every square has to commute. This is a very, very big commutative diagram. And if it is, then it respects the structure of the representations nicely, and then it's a morphism. And this can be encoded in a group action again. So we call it GD because it corresponds to the dimension vector, and it's the product over the GLDI at the vertices. So GL of C times GL of C squared, and so on. And then this action is change of basis in a way that we just saw. So this is an example, but you get the gist how this works in general too. And then for our purposes, this variety is too big. We fix a subvariety, and this is what I meant when I said the flag. So we call it RD0A, and it only connects those tuples such that from the left to the middle, here, 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 we are injective, and then from the middle to the right, we are surjective. Like this. And again, we have an action. So injective. And this is the flag condition, which in our translation will inherit the Borel structure. And now we can prove the lemma. And it says that the B orbits in M2 are in bijection to the GD orbits and RD0. So this is what we want to know. And now we go back for a step. And we can see that this is the representation category. This is the representation variety. And we are interested in this action. Okay. And the orbits are the isoclasses in the category. That's exactly how we defined it. And then for the closures, we will select.
And then can I interrupt and ask a question about the notation here?
Yeah.
You have L, which is different from N, but it seems like L should be N-1 or something. Or
No. N is even or odd, and then it's 2L plus 1 or 2L.
Oh, L is the actual rank of the eventual classical group.
Yeah, exactly.
So, okay.
Yeah, of course. I mean, we could start with the usual flag and put the loop at the end, but we want to go further to the symplectic and orthogonal setup, and so we have to split in the middle.
I see. Yep. Okay. Understood.
Okay. Perfect. Any questions? I mean, you just interrupt, right? Okay. So we have this connection, and what's behind it? It is an associated fiber bundle. So we have RD0 is isomorphic to this associated fiber bundle, GD times BN2. And actually the construction is very nice. And I can mention that I put in some kind of a literature list in the end, because we use many basic work and stuff. And so if you're interested in this, you can look it up. And of course I can send the slides. The nice thing is that this associated fiber bundle construction is geometric. And this means that we are lucky, it preserves orbit closure relations. This is not just any bijection, but it's a strong one. It relates, for example, types of singularities and certain dimensions of stabilizers so that we can transfer dimensions. This is very nice. And the orbits on the left-hand side, they correspond to the isoclasses of representations. And this is an explicit bijection, so we know how to translate. And The closure relations, they correspond to so-called degenerations. And so these are the things we need to understand now: isoclasses and degenerations. And in type A, we can make use of representation theory, as we saw, and this is very well developed for our purposes in type A. Okay. And so this is done. Now we go over to the classical types, and this means we have to, or we want to, because it's an advertisement, look at symmetric quivers now. Because for this translation, we need symmetric quivers. So let's define them and see what they can do. And this is symmetric. Ah, yeah, you see, I put this this weird bar on the left. Now you see, red means types B, C, and D. Yeah, I mean, it's fun to draw on these slides, but you can also ignore it. Okay, we fix a finite quiver, set of vertices to 0, set of arrows is Q1, and now we consider a map sigma, which is defined on the set of vertices and the set of arrows. And what is this supposed to be? On Q0, it's an involution. So it sends Q0 to itself involutively. And then Q1, it's also an involution, but it reverses the arrows. So it's an anti-involution or reversing involution or arrow reversing involution. And this means if we have an arrow alpha from I to j, then sigma of alpha goes from sigma of j to sigma of I. We will see an example. So, and if we have something like this, Q and sigma, then this pair Q sigma is called symmetric quiver. And we will keep the sigma in mind and just call it Q again, but we have a symmetric structure now. If we say Q is a symmetric quiver, then this means Q sigma. So maybe two examples. First one is this. So this is a Dinking quiver of type A5, and it's linearly oriented from left to right. And so this corresponds to this to this. So we see that it's an involution on the vertices. And now are the arrows reversed? This we have to check. So alpha from 1 to 2 goes to sigma of alpha from sigma of 2 to sigma of 1. That's fine. And the same for this. So this is all okay. We also have a self-symmetric one or self-dual one in the middle. And now if we put a loop in the middle, then it's still symmetric if we say that psi is sigma of psi. So also our quiver from before has a symmetric structure. And another one, so it doesn't have to be linearly oriented. Here we have a self-symmetric arrow in the middle. It's also fine. Okay. Now, what about the path algebra of some symmetric quiver? It is defined, but we need some assumptions. So if the path algebra of Q is CQ as before, then we know that the sigma also extends to paths because it turns around the orientation, and still we can concatenate in the same way as before, just turn around. Okay. And then we fix an admissible idea. So that means, kind of means, somehow like this. So there is a case such that all paths from a certain length are inside of I. So we don't have infinite loops anymore or infinite cycles. That's the idea. And this, I know it's gone. Is that clear with the admissible?
Yeah, that's clear. There's a question about the previous slide, actually. Could you just go back to the previous slide for a minute? Sorry.
Yeah.
Okay. So that's you've attributed the notion of a symmetric quiver to DW. Is that Derksen and Weyman?
I forgot to mention. Thank you so much. Yeah, of course. This is Derksen and Weyman. They define these quivers. I mean, I will not mention them later, anyways. But yeah, this is their definition. It was 2002 when they defined these quivers. Exactly.
Thanks.
Yeah. Thank you. It's a good question. Okay, and this admissible idea has to respect our symmetry. So sigma of I is I. I is a symmetric idea. And if this is the case, then we define our quotient algebra. This is the same as before. And it's again finite dimensional, associative, size one element. In general, it's not commutative. That's just here because it's a path concatenation. But it has structures. For example, we note that sigma induces an isomorphism of A to itself. We're going over to the turned around algebra, but it's a nice isomorphism. And this induces a self-duality. This is important on the representation category. And I won't define it, but I mean, it's induced by sigma and by the usual dual. And we put in a minus at some certain point. And it makes sure that we go into the Lie algebra with everything, or into the Lie group with the isomorphisms. And this is why these algebras are also referred to as algebras with self-dualities. Now we fix certain data which we just need because we look at orthogonal and symplectic things and at representation. So we start with the dimension vector and also symmetric one. So di equals d sig y. And then we fix the graded vector space as before. So this is the direct sum of the vector spaces at the vertices of the quiver. There's the sum there. And now, of course, we want to work symplectically and orthogonally, so we fix a bilinear form. And this means we fix a non-degenerate bilinear form on V. And also this has to be compatible with our symmetry sigma. And what does it mean? If we restrict it to two copies of the grading, Vi and Vj, then this is nearly always 0, unless I and j correspond to each other via sigma. Okay. So this way, later we are able to give Vi plus V sigma I a symplectic structure, for example. And second, it's an epsilon form, so it's symmetric or anti-symmetric, depending on the sign. And we need these data. I try to avoid using them all the time. I want to show you how we work in representation theory. Still, of course, they're behind everything. That's clear. I mean, we go over to the classical types before. Representation theory and typation theory in types B, C, and D. And on the left, we already saw that representations are given by tuples of by tuples of C-linear maps. And there is the change of basis action by GDs, which is only the direct product of the GLDs, and the change of basis action is this commutative diagram which we saw. And also for every other quiver you can define it like this. Now we want to make this symmetric. And this means we define epsilon representations or symmetric representations. And if epsilon is 1, then we say they're orthogonal. And for epsilon minus 1, they are symplectic. And they are also encoded in a variety. And this variety only collects those representations such that M plus its adjoint with respect to the form is 0. So we just smash in the form, something very natural. And you'd say, yeah, but how shall we work with this? I mean, I don't want to put the form in every representation. We will see, okay? But this is the natural thing to do. And then the change of basis action is also defined. So we define it as GD epsilon and collect only those base change elements that respect the forms. So GV, GW is VW, or G is the inverse of its adjoint. You can call it like this. And if you define it like this, then first you have the notion, okay. Secondly, you get the translation, exactly what we want, and also due to these self-dualities, you are able to work with these because it all fits together in a certain way. Of course, you make sign mistakes every time, but have to get into the picture, and then you can work with this nicely. And so the first thing I want to show you is how we can use this symmetric representation theory in order to approach our classical problem, so that you see that it's nice to have. So let's look at this. So let's see at the translation in the classical types. We fix the same quiver and the same relations and the same dimension vector. This was already done in a way that we can use it now. And then here below, we see the action we looked at before. And now we want to make it classical. So we just put it in the classical stuff. We see that the quiver already is symmetric, as we saw in the example, and also here. Left corresponds to right, and the symmetric axis is here. Doesn't draw. And the relations are symmetric. Okay, they're nicely symmetric around the middle axis. Yeah. And the dimension vector is symmetric. Look at this. And so this should be fine in order to define symmetric representations. So as before, we fix a sign, we fix a form. That's the same. We need it. And then we say that RD epsilon is the variety of epsilon representations as defined in the last section. And of course, then we need to restrict RD0 to the epsilon representations. And that's the variety we work with. And on the left-hand side, okay, these are the symplectic orthogonal epsilon representations of this quiver. And on the left-hand side, GD epsilon group as before. And then we have actions. So this is the same, but for this example. And we can translate. So in type A, this is the translation. B orbits in M2 are in bijection to GD orbits in RD0. And that's an associated fiber bundle construction where this is given by the flags. So the tunipotency is inherited in the quiver, in the tunipotent loop. And now we do the same with the epsilon stuff. Whoa. So, okay, I put all in at the same time. So note for self, next time do it more slowly. So we see, this is the one we had before. And now this is the new one. So look here. The BG orbits in NG2. So this is the difference. And what do we do on the right-hand side? Of course, we use the action which we just defined. So GD epsilon orbits in those. It's the same. And also, the associated fiber bundle is the same. The construction is the same. It's just everything is restricted to epsilon representations. And in classical types B and D, epsilon is 1, and in the C type, epsilon is -1. And the orbits are given by isoclasses of epsilon representations now, and the closure relations we will look at later. And so in this case, we make use of symmetric representation theory. And now I can't say well developed for our purposes because it's just not. But so we figured this one needs to be developed by us, which of course, as first you want quick results and you think, too bad, but actually it's a lot of fun. And yeah, that's what Giovanni and I work on now. We try to develop further what's known about symmetric representation theory. And that's the picture so far. And then after the break, we go into methods, degenerations, and results. Questions?
Quick question.
Go ahead.
Construction of the associated vector bundle. How does the Borel act on GD?
Mm-hmm.
Yeah.
Wait, we go back.
Just go back to the slide, yeah. There you go. Yeah,
we can go in type A, right?
For instance, yeah. My question is, how does the Borel act on GD?
Yeah, it's so you can interpret the Borel as a subgroup. Actually, you embed it into the product by actually like a flag, and then you have the usual GH inverse or GB inverse action.
So it's embedded inside GD like a flag. Okay.
Yeah, you embed the first block into the first component, and then the second upper block into the second, and so on, and then everything commutes fine, and exactly, and then you have the natural action.
Yeah, sure. Okay, thank you.
Welcome back. Thanks for coming back. This is the picture so far. So let's just quickly review. On the left-hand side of the picture, we have the Borel actions on the two nilpotent matrices, either in type A or in the other classical Lie types. And what we found out was that we have a translation via an associated Ferber bundle to isomorphism classes of quiver representations or epsilon representations and their degenerations. We want to study orbit and closure relations. Okay. And now what we do now is we study representation theory and symmetric representation theory in order to answer our more about this. So we start with methods. This will answer the first question about orbits right away. Then we look at degeneration. So what is it? What describes our closure relations? What do we know about them? And what did we find out? And then in the end, results. Okay. So first methods, which is very common, is the theorem of Kohlriemann-Schmidt, and I just recall it. So this theorem states that every representation in RD decomposes up to isomorphism into some unique direct sum of indecomposables up to reordering, of course. And these indecomposables, they do not decompose further. And this means in representation theory, we have to understand the indecomposables. That's just what we have to do. And then, of course, this is difficult. It's not like you have a curve down the indecomposables. That's not easy. But we are very, very lucky that we have a theory which helps. And that's Auslander-Reiten theory. That's what Giovanni just said in the break. So what is Auslander-Reiten theory? It's a big theory. So it's strong and it's beautiful. And I want to tell you what the main ingredient is. And then if you want to get into it, then we can talk. So the definition of the main ingredient, that's the Auslander-Reiten quiver. It's again a quiver, and it's called gamma A. And it belongs to the algebra or the quiver with the relations. And this is a quiver, so we have to say what are the vertices. The vertices are isoclasses of indecomposables. So the vertices are what we want to understand. If we know the quiver, we know the indecomposables, the Auslander-Reiten. And the maps are certain minimal maps. So you think of this Auslander-Reiten quiver as a way to model a category. You want to model the category, so you need to understand the minimal objects and the minimal maps between them. And that's the Auslander-Reiten quiver. And so yeah, I wrote this down. It's amazingly beautiful. It was developed first by Auslander and Reiten, and then further and further developed by many people. So I won't list them because I will forget someone. This is not good, and it's not to be explained in 10 minutes, and it shouldn't be. But I want to show you how it helps. Because this Auslander Reiten quiver has a very, very, very nice structure, and this is given by meshes. So it's a quiver, it has vertices, and it's made up out of meshes. And these meshes look like this one, for example. We have one indecomposable on the left, one on the right, and one up to several in the middle. And then from the left, they are exactly linked by maps as to the right. And these methods of meshes, of course, they have homological ideas behind them. They're almost split sequences. So a certain kind of exact sequences which kind of inherits all the structure of the indecomposables. It's very, very nice. And since these almost split sequences were studied a lot, for example, by Auslander and Reiten, we have certain techniques how to calculate this. So one of these calculation techniques is the knitting algorithm. And I mean, you see these meshes, and so you think of knitting. You knit from mesh to mesh as if you were knitting a pullover. And nicely, you have a very nice possibility to describe the projectives and the injectives indecomposables, and then you have dimension formulas, and you knit and knit and knit, and so if you're lucky, this finishes at some point, and then you're done. And if you're not, then of course it's more likely, because there are many very difficult quivers, and of course you cannot accept this to work always. Then, for example, there are covering techniques. For loops, this is very nice. You grab your loop and you cover it by an infinite covering quiver. You just, I mean, you have this covering picture. You would just, in German it's auseinanderziehen. I don't know the English word, so you just make it a long line.
Unwind, maybe.
Unwind, maybe, yeah. And then, yeah, there's a nice article of Gabriel about this. And then, of course, you can calculate almost split sequences. It's is explicitly described how to get these meshes. So there are many ways. And yeah, in certain cases, this determines the whole Auslander Reiten quiver. For example, for the drinking quivers, and also for our quiver, which we just saw. And so I want to show you one. So this one. This is the Auslander Reiten quiver of the quiver which we just looked at, but now n is 7, I guess. Yeah. So we have 1, 2, 3 vertices going in, and 1, 2, 3 going out, and in the middle we have the loop. And so I can draw. Here we have the projectives. See, so you draw them on the left, you calculate them, draw them on the left, and then you start the knitting. This works fine because you know the radicals of the projectives, and this, I mean, it's a large theory, but you see that you can just, you go over to this, and then to this, and to this, and then to this, and so on and so on. And there are many different types of Auslander Reiten quivers. But this one is special because first it's finitely many indecomposables. That's good for our purposes. And second, okay, these are the indecomposables, the vertices. And second, we have to identify these. So this is the same as this, but it's the same indecomposable. It's not another copy or so. It's the same indecomposable. So in the quiver, they have to be identified. And this means we get like this twists around and have to glue this together. So we have oriented cycles in the Auslander Reiten quiver. This is, yeah, this is interesting. I think this is just interesting. So we have exact sequences going in and out, and we have to be careful whenever we study this. And now let me show you a picture, because sometimes a picture says many things about the symmetric structure of the Auslander Reiten quiver. I mean, you kind of see where it is symmetric. And it is. So this is the symmetry of this Ausländerreiten quiver. And it's given by nabla, by the self-duality on the vertices, on the quiver, on the representation. Sorry, it's very early. So it's the self-duality on the representations. So in the middle, we have the self-duals. And then always we grab one from the left. And then the nabla is on the right, or the other way around. So the indecomposables for the epsilon representations, either we grab one from the left and the right and we add them up, or we grab one in the middle, or two copies of the ones in the middle. And then we have to be careful that they have symplectic and orthogonal structures. Okay, but the Ausländerreiten quiver inherits a lot. So you see where you have maps, where you have exact sequences and so on. Okay. And with these ingredients, we can talk about orbits. So if our task is to classify the representations in RD up to isomorphism, so our task is the orbit classification, then of course we classify the indecomposables up to iso, that we do with the Ausländerreiten quiver. Then we add them up to the dimension vector D in all possible ways. And then 3, of course, we try to interpret it combinatorially. We want to find something nice which corresponds. And we will see pictures in the end how this works in our case. And this way we get a parametrizing set. Good. So type A, fine. And then in the other classical types, so RD epsilon, we do the same. We classify the indecomposables in RD. And then we just restrict them to RD epsilon, so we make this nabla construction. We add them up in a certain way. And Derksen and Weyman described what the indecomposables are in the different settings. And they also said that the orbits are induced. So they are isomorphic as representations if and only if they are isomorphic as epsilon representations. This is perfect for us. We don't have to think about this. There's always an isomorphism. And so the orbits classification is kind of done. Of course, then you have to write it down and work on it. But the general picture is kind of well understood.
Can I just ask a question about that? That result is presumably in the version where if you have epsilon equals 1, you have orthogonal groups. And it would be slightly more complicated if you had special orthogonal groups.
Yeah, exactly. We only work with orthogonal groups.
Okay, yeah.
Yeah.
Can
Questions?
Can I just ask quickly, how does the picture on the previous slide sit inside the derived category? So is there...
Yeah, and then you have to, I never worked with derived categories, but I mean, how do you do this? You twist it around and then you make copy after copy?
So this is hereditary? So is every complex in the derived category, is every indecomposable complex isomorphic to a shift of one of these?
Oh, this I don't know. I never looked at this. Because I never worked with derived categories and not with complexes at all. So I don't want to tell you something now.
Well, that's an algebra of finite representation.
Maybe we can discuss it after.
Yeah, so it should be true. I think. Yeah, I think so.
Yeah, we can double check. More questions? Because this is really interesting. This.
So how does the structure of the quiver go into the steps you outlined in the next slide? Because it seems like you just used the vertices of the quiver, the fact that you know how to classify the indecomposables.
Well, no, you classify the orbits, and then you only grab those which always have one copy of the M and the nabla M, for example. So you have to see if that left and right correspond to each other, because otherwise it's not an epsilon representation. Mm-hmm. Pick one of the left, then pick one of the right too. And if this is not the case for every indecomposable, you throw it out. Then it's not an orbit for your epsilon structure. Exactly. So it really helps. Yeah. Okay. So methods done. Degenerations. Let's see. What is a degeneration? We are in type A now. We grab two representations and we define three partial orderings. Degeneration ordering. That's called deg, so, well, like degeneration. And this is the one we need, orbit closure relation. And okay, closure relation. Yeah, I like this with the colors. And you have to see that this is turned around. So here's the n and there's the n. And then later you see why. So the closure in relations are defined to be the partial ordering degeneration. And then this is, and now this is difficult to describe because what can you do to prove orbit closure relations? I mean, you have to find some curves, but I wouldn't want to define curves for going everywhere all the time whenever I have a closure relation problem. And so many people worked on this, and they were they proved very nice results, and they defined another partial ordering, and that's the Hom ordering. And this is defined by dimensions of Hom spaces. So something which is often easy to calculate. I mean, at least if there are not too many indecomposables. So you just grab the dimension of the Hom space from U to M and the one of the Hom space from U to N. And if the one is smaller than the other for every indecomposable U, then you say these representations are related in the Hom order. If you haven't never seen these definitions, maybe don't look at what's written, but think dimension of Hom spaces. That's not too bad. So that's the Hom order. And we have a third one, and that's the Ext order. And the Ext order is given by extension. So representations, there exist representations and short exact sequences such that the outer terms of the first exact sequence add up to the middle term of the next. And then again, the outer part adds up to the middle term, outer, middle, and so on. And if we find like a tower of exact sequences like this, such that the first middle term is M and the last is N, then we say they are comparable in the Ext order. So this is kind of the transitive closure of having an exact sequence such that the outer terms form the N. Ext order. And now you might think, so what? I mean, of course, the Hom and the Ext are nice because we know how to construct exact sequences with the Außenseitenreihen quiver. We have some techniques. We know how to calculate dimensions of Hom spaces, but why should we care? And then let me tell you that there's a general, in all generality, if we have an Ext, then we have a degeneration, and then we have a Hom. The first was proved by Bongartz, and the second was, so the theory was started by Abiazis in type A rank conditions, and they worked further on type A with different orientations, and then Riedmann, she made it into this Hom order and proved this result. Okay. Then there's another important case, that's the Dünking case. So if the graph underlying of Q is a Dünking quiver, and then it was proved that they are all the same. They all coincide. This is very nice. This is due to Bongartz. So in the Dünking case, the orbit closure relations are just very well understood. And then there's the one that we have here. So the number of indecomposable isoclasses is finite. And even then, there's hope because Zwara showed that the degeneration and the Hom are the same. And so we have this picture in type A. It's very nice to calculate orbit closures because we just write down the Hom and we're done. This we can do, and we did. So This was partly what I did in my PhD. But in the symmetric setup, it's not known, or it was not known. And this is where Giovanni and I started when we worked in Rome. So let's look at the symmetric setup and try to do something like this. We want sufficient conditions. We want necessary conditions. Somehow we want to understand orbit closure relations. And symmetric degenerations, let's see. We have to define some orderings. Of course, we grab the same, and now we adapt them. For the epsilon representations, epsilon degeneration, that's fair. That's orbit closure relations again. Then the HOM, we think that it's the same. It should be the same HOM ordering. But for the Ext, so this is the Ext order which we developed. First, of course, it's called epsilon Ext. We grab epsilon representations. And still we have this, I don't know if tower is the right word, but we have this tower of exact sequences, and they add up in a certain way. But now this embedding has to be isotropic. So the image has to be in the orthogonal complement. And we start with M and end with N, that's the same. And then, so the middle term adds up differently. We have to put in the form and the isotropic structure. Okay. If you start working on this, this is something very natural to do. And now I show you why in the end we were convinced that this is the right thing to do. Because in the general case, so in our generality, we were able to show that if we have an epsilon X, we have an epsilon degeneration. This is an explicit curve construction, which is an epsilon isomorphism. And then also we have the HOM. Yeah, for the other types, we look at results now. So we have quarter of an hour, so let's see how far we get, but I think this will be manageable. Questions to the degenerations? Or about the degenerations? Okay, then I wanted to because this is we start with our paper now. This is one of the first results which we had. We have a symmetric Ext order. We were already very happy about this, and so now let's see about the results in the other types. So in the other cases. That's a picture of Giovanni and me yesterday when we submitted the article to the archive and talked to our friends about this. Just a stupid picture I found, but I like it very much. Let's see, in the Dinking case, we have a connected symmetric quiver, and this is of finite type. Finite type means finitely many isoclasses of indecomposables. Okay. And then Derksen and Weyman show that this is only Dinking type A. This is the only one. So we only have to consider Dinking type A, but I mean, it's enough. And then we have the path algebra, we fix the sign and the symmetric dimension vector. So everything we just needed before, but that's the setup now. And then there's the theorem. I don't have the archive identifier now, but it will appear today, so there will be one. And the theorem says, if we have two epsilon representations, then we have an Ext relation, if and only if we have a degeneration, epsilon degeneration, if and only we have a degeneration, and that's the same as the HOM. Okay, so it's exactly the same result as in the non-symmetric case. And in particular, this means that the degenerations are the same, so it's induced, in fact. Of course, we can ask the questions, the orbits, and not only for the algebraic question. And in this case, orbit closure relations are induced by simply restricting. Okay. Now, we won't be able to understand the proof in detail because the article is 40 pages and we use Ausländerreiten theory throughout the whole article. So, but I want to sketch the structure so that you see what the ingredients are, okay? And the strategy of the proof is the strategy is, okay. Okay, now it works, sorry. We need to show that if we have a type A degeneration, then we have an epsilon extension. So that's the only thing left. If we look at this, if we have this, then we have this. So that's done. That's done. That's always clear. So we have to go back. And that's what we do. So if we have a degeneration, we have to show that we have an epsilon extension. And so if they're isomorphic, then we're done already. But if we have a proper degeneration, then we go by an inductive argument, by the total dimension of M and N. If they have total dimension 0, okay, that's fine. But if it's bigger, and then we grab some direct summand, indecomposable, such that there are no extensions. And this is fine because A is representation directed. This does not work for our motivating example because we have cycles in the Ausländerreiten quiver. This will be a lot for the experts now. So if you're not, then try to get the big picture, okay? Then we have a theorem of Bongart's that shows that we can embed L into M, and without loss of generality, this can be chosen generically. So that means that the quotient of this is generic in the set of all quotients. And now we go on by case study. So either L is isomorphic to its nabla, it's in this middle axis of the quiver. Then we grab the corresponding epsilon representation. This can be L, or it can be 2 copies of L plus nabla L. And then we say that N is X plus E, okay? And then by a theorem of Bongart's again, we know that E embeds into M. So you see that we use a lot the proofs of the type A constructions. And then we know that the generic quotient degenerates to X, and these are smaller of dimension, and the induction hypothesis applies, and we are done already. This is quickly done and uses strong work of Bongart's. In the second case, when L is not isomorphic to nabla L, then again we write N as a direct sum like this. And again, we have an embedding, and then we need to show this, that it can be chosen isotropically. So we have to define certain base changes which make this possible. And there you see that it gets technical. And then we define something which is called the generic epsilon subquotient. I mean, we say that it's called generic epsilon subquotient. It's the orthogonal complement, the quotient by the image of this generic epsilon subquotient degenerates to X. And then we are done because of the induction again. So X and Y are both smaller dimension. So then it's done. And for this, we need 3 ingredients. And also these ingredients are big propositions. We need to define, to know what generic quotients look in general. And in type A, we describe them in our generality. And also explicitly in the Ausländerreiten quiver. So we say, if we have a generic embedding, the quotient is this, this, and this indecomposable. Okay, it's constructed. We need to define, we need to understand what these generic epsilon subquotients look like in terms of the generic quotient, so also in the Ausländerreiten quiver. And then we use Suarez' result that the degeneration is the same as the Hom, so that we can actually prove this by explicit construction. Okay, and then we're done. And this is hard work, and this is also a lot of fun because it's constructive, and it's also nice. And so in particular, what we what we get from this proof is that we can actually construct flow pictures going from one representation to the other. And this is an example for such a flow picture. So we have M and N, and now we describe certain steps: degeneration, 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 degeneration. So we grab the L, which we had in the beginning, and then we are only we embed. So this is the embedding into the M. We draw it into the quiver, and then we calculate the Y, and it's this. And we add the Y, and this goes. So this is how to describe them. These flow pictures can quickly be drawn. And this way you can go from M to N always. Okay. And so, I mean, if you really want to get into this setting, then this will help a lot. And this is the drinking case. We are very happy. It was not clear that it's induced, but it is. And we thought that it would never work several times. And I'm lucky that Giovanni kept working while I was on parental leave, and had some great ideas, and now we were able to finish this. And yeah, if you like, have a look. And so in the end, I will only quickly tell you about the motivating example. That's some representation finite type, which has a nice twist in the theory, because so far everything worked out the way it was expected to be. And now we see that in general, we should expect also different things to happen. So this is the quiver. We remember we grab a very small example now. So 05, SP4 and 04. The dimension vector so has a 5, 4, and 4 in the middle. And now let's look at this. We can classify the orbits. That's what I already said. So these are the orbits. And we found nice combinatorial objects for these, which we call oriented link diagrams. I see that somehow PowerPoint got rid of the orientation. PowerPoint is not mathematics friendly, I think. But these are not only, these are arrows, okay? So of course, otherwise these would be the same. These are arrows. I don't know where the orientation is. And okay, so we have the orbits and we classified them in a way which I described before. And then we know that the degeneration order is the same as the home ordering. So we only have finally many, we just draw it in. So this is the degeneration order in type A. And next step, we want the epsilon degenerations, but we don't want to define curves everywhere. So we started with calculating the dimensions, the epsilon dimensions, or dimensions in the epsilon representation variety. And now let's draw them. These are the ones, 2, 1, 0. This seems to be fine in type C. And then in type D, can you hear me?
Yes, I can hear you. You dropped out for a little bit, but you're back now.
Okay, perfect. In type D, we realized, oh, something we calculated, I think these dimensions we calculated around 25 times, but still they're the same. So we see this. They have the same dimension. In type A, they degenerate, but now they have the same dimension in NG epsilon. This is not so good for a degeneration, because orbit closure relations, I mean, we always go to a smaller dimensional orbit. So this will not be a degeneration in type D. And so it's a degeneration, but not an epsilon degeneration. And this is our counterexample that it's not induced. So There it is. Okay. So in this case, we calculated by hand. And this is the diagram now. It has two irreducible components. And this is kind of expected because it's type D. So it makes sense that something weird happens, but it also shows that it's not induced. So if we put this into the general picture, so here, then we see that for our least theoretic problem in type B, we don't know. In single G orbit, it seems to be right. So if the rank is the same, we seem to have the same degeneration order. In type C, it's true. It's in preparation. We work on it. But in type D, it's not true. And there's always a counterexample for every size. Okay. And now the conclusion for the epsilon degenerations in general. What do we know so far? In general, if we have an epsilon x, we have an epsilon degeneration, and then we have a Bochum. So sufficient condition, necessary condition, that's done. In the Dinking cases, we know that they're all the same. And then in the finite reptile, we have an example that it is not true in general. And so we conjecture that here, it seems to be fine on the irreducible components. No, that's not true. That I have to delete this. Anyhow, so we are not sure. Bigger examples produce bigger pictures, and then at some point the curve calculation is getting very annoying, and also the extensions, and so it's difficult. But we have a conjecture for the representation directed case. So when we have no cycles in the Ausländerreich quiver and only finitely many representations up to isomorphism, then we expect them to be equivalent. So this might be the next step. And I think since we use in the proof that we grab the summand because it is directed, it's an educated guess. Okay, so that's the literature list. If you have questions about some results, then yeah, thank you.
Thank you very much. There was one question I wanted to ask when you were talking about the Dinkin case. If you now apply that result, can you deduce something you can express back in the same sort of language as originally about orbits of parabolic subgroups on particular subvarieties of the nilpotent cone?
Yeah, we started. I mean, we were pretty busy with the proof, but we included, for example, what were we talking about? For example, I draw it here. If you have A2. And then you say, here you put Cn, and here you put Cn, and then here you have a map. And you make this symplectic, then you can see that the congruence relation, so the orbits are defined by the ranks. The congruence orbits of this, how do you call them? Congruence classes, maybe?
Sorry, I'm not sure what you mean. You can
Yeah,
say it in
then I have
German
to
and
write
Jordi
this
can
down.
translate.
Congruence class. No, I think it's, well, let's see. Maybe we can write this down in maybe a little bit more detail. Do we have time? Because I only see that 9 o'clock is done, but that should be okay. Let's see. I want to use the language of the article, and then it will be nicer. So, okay. If we have some time, then I sketch it in detail.
Lena, just a very naive question. So what led you, so you and Marcus first showed that there was finitely many orbits on two-step nilpotents. Do I understand correctly? That
no, we didn't show that there were only finitely many. This was known by Panyushev, but we classified them.
Ah, okay. And is there some reason to believe, like, is there some, like, is there a good heuristic for why there should be finitely many? Or because often, I don't know, often I find that I come into some situation and I want to know whether there's finitely many orbits or not, and it's generally very difficult. Do you have some way of like deciding, like guessing well?
Well, since I'm from representation theory, my guessing is always a look at the quiver. But then, of course, it's a guess which needs work because you need to understand the representations. But if you know the quivers and then you know the Auslanderreiten theory, then you get a grip on it. Only for the, I think if you look at the, for example, parabolic actions of some variety, something like this, then just by looking at the action, I think then you have to ask the Lie experts because they have these, yeah, I don't know what the techniques are in detail, but Panyushev's work, I think it's a reference because he classifies many finiteness criteria. But of course, I mean, if you translate it to representation theory, and there are many translations possible, then yeah, then you get a grip because there are many classificational works, and not only on finite web type, maybe it's a tame problem. It's also nice to know if it's a tame problem, or even if it is wild, at least you know. And there are lists. If you have a quiver, you look at the lists. If some is included, it's tame. So there are many possible approaches.
Thanks.
Maybe let's all join in thanking Lena for her talk. Bye, everyone.
Thank you all for listening.